Here we have a young synthetic biologist about to use dSign, a web-based signature encryption and insertion method. They first start on the homepage where they can read a little bit more about what dSign has to offer. They also have the ability to watch this exact video. They're able to see and interact with the homepage thanks to this PHP and HTML script. The HTML creates the interface that the user sees, and the different PHP scripts are called depending on the buttons clicked. The following functions check to make sure that a user is logged in and ensure that the same session is used during the duration of the login period. If a user is not logged in, they are directed to the login page. Lastly, a user ID is randomly generated for each user upon creation of an account. This file simply ensures that the connection to the database where all of the information is stored is secure. Quickly shown is the database used to store the user's inputs when they interact with dSign. The next page the user clicks on is the FAQ page. Here they can read about the history of dSign and its creation, how to use dSign, the different types of signature placements, where to find the export files, how guest access works, and all of the limitations of dSign's current versions. Quickly shown is the HTML code that generates the FAQ page. Here a user creates a dSign account. The username must contain characters and the password must be exactly 10 characters long. Shown here is the PHP and HTML code that generates this page, reads in the user's inputs, and saves them into the database as a new user. The username is also checked to ensure that it is valid. The user is then directed into the login page where they log in using the username and password just created. The information the user inputted is checked to make sure it matches the information in the database here. If not, the user is told that one of the inputs is incorrect. The user is automatically directed to the profile page. It normally shows the sequence uploaded, but it is empty currently since the account is brand new. The user then goes to fill out their signature information. This includes their name, email, and location. There are links to find their school and NASDAQ codes. Here the user clicks on the link to find their school code. The information the user just inputted is queried into the database with this code. Additionally, the information as well as the password is put into a JSON file used for the encryption script. The signature inputs and the password are extracted from the JSON file, and the extracted information gets put into a class. The function combine_array indexes the password in a list format to be more accessible and to be sorted into ASCII order later. The institution type is shortened to Uni for academia and IND for industry. A list is created with all of the signature inputs that are fitted into an array. The ASCII sum of each column is found and divided by the ASCII sum of the 4 nucleotides. The lowest remainder is used as the nucleotide translation of that column. The signature is then reordered to match the original password. After the signature encryption, the user can then add new sequences to their profile. Here they are uploading a reversible DNA sequence. This is intended for computational work. The characters of their signature after being translated into nucleotides are randomly positioned in their DNA sequence. The alternative is irreversible, where the location is specified by the user, and that is where the signature is placed. Here you can see some parts of the signature placed within the DNA sequence. Here the script shows that each sequence and all of its information is queried into the database. The sequence information is then placed into a JSON file. Depending on the encryption type, the appropriate Python script is executed. The user first chose a reversible encryption type. The main function in this script is reversible spacing, which first separates the signature and sequence characters and saves their respective lengths. The first location is randomized from 0 to an integer value of m to ensure that there will be a larger spread in the signature throughout the sequence. A new number will be generated between the current largest number in the list num and the value of m to replace the old number. This process will be repeated until the new number satisfies the requirements in the while loop. Final, which is the sequence with the randomized signature character locations and the list of locations, is outputted. The other encryption type is the irreversible type. Here the main function is non-reversible spacing, which places the signature as a whole with a primer for the type 2 restriction enzyme in the front and the back at the location indicated by the user. It will output the DNA with the signature in it and the location of the signature with the primers attached. Both scripts have the same formatting functions. A function that converts the DNA with spaces into a string of only characters, and one that converts the signature and sequence string to one with spaces for every 10 nucleotides. The following script is called DNA encrypt, and it has another JSON file that is read to extract the information and variables needed. Using a key derivation function, we initialize its characteristics to have a hashing algorithm, a length of 32, a randomized salt, and iterations of 390,000. After the function is initialized, it uses the input password that is made into bytes format to derive a key of base 64. This will be written in the public key file. The key will be then converted into a fernet type key. This fernet type key is the one that will encrypt a bytes format message that includes the author of the sequence, their email address, the institution code and institution type, a description of the sequence, and the sequence with the signature embedded in it. This is written in the token variable, which will be outputted as the datacode.key file. The user now inputs the same sequence but chooses the irreversible method. The signature in the primer sequence for the restriction enzyme can be seen within the sequence at the user's specified location. This code detects what button is pushed. If the send button is pushed, it writes to a file that will hold the guest access key. The export button writes to a file with all the sequence information that the user wants to themselves. The delete button deletes all of the information corresponding to the sequence from the database. Shown here is the exported file for the user containing the reversible sequence information. Shown here is the exported file for the user containing the irreversible sequence information. The user deletes a sequence to show that they can. The user then decides to share their other sequence. The user then clicks on the two files generated that they would share to another person. The first file is the encrypted DNA sequence with a signature, and the second file is the access key. The user returns to dSign and logs out. They proceed to go to the guest access page to confirm that their share files work. They upload the access key and the data file containing the encrypted sequence. This file executes the decrypt script and gets the sequence information. In the decrypt function, these inputs are then read. The public key is changed into a fernet type key to be able to decrypt the token or encoded message in the datacode.key file. It outputs the sequence author's information. Shown here is the decrypted sequence and message. Here is a quick look into the now filled database. The user then returns to the homepage, feeling proud of a successful signature encryption, insertion, and exportation.